Hello, everyone. I'm Naveed Sonola, and thank you for coming and listening in on my talk about binary AST. So I think we're one slide ahead already. All right, there we are. So binary AST is a new technology that my team has come up with to turbocharge page loading in the web. And the question is, why do we need this new technology? And the answer to that, we want to go back 10 years in time using the Wayback Machine and take a look at the Internet of the yesterday. So here we have a popular financial portal called Bloomberg. Back in 2007, I think I got this from the Wayback Machine, and it says it's March 2007. If you look, it's probably a typical website of the time. Static content, very little interactivity. When interactivity is there, is provided mostly by Flash. This was acceptable back then because we didn't expect more as users of the web, and so we were content. But we have come a long way. In the following 10 years, many things have changed, and what would be acceptable back in 2007 for a website is certainly not acceptable anymore. We want more from our websites. So here's Bloomberg in 2017. We have a far more beautiful, interactive site that has tons and tons of content that caters to you as you interact with it. I put together an animated GIF, and you can see it's slowly flashing between some of the content areas and the things that you can do, but it doesn't capture the full capacity of the site today. All this interactivity, though, comes with a big cost. Here we have a depiction of the JavaScript code that the site used back in 2007 and the site uses today. Back in 2007, we were using about 100 kilobytes of script, and today it's almost a megabyte, 9 times more. Bloomberg is not alone. In fact, it's not even the largest of the top sites. Wait for this to catch up. So if you look at the little blip on the far left, that's the amount of script Bloomberg used back in 2007. That's, once again, 100 kilobytes. Bloomberg in 2017's the red square on the far left, and that's only a megabyte. But the big players, the top sites on the web internet, are using 7 megabytes or more, like LinkedIn and Facebook. And this is already minified and compressed source. Does script size matter in 2017? Everything is faster. The internet's certainly faster. The servers that deliver us content are quicker. We have CDNs that distribute that content delivery. Our computers are faster. We have really fast CPUs, and those CPUs have many, many cores. And JavaScript implementations have gotten smarter and better. Today's JavaScript engines are 10, 20, 30 times faster than they were back then. However, we've become more impatient. Our expectations have increased, and our tolerance for page loads have decreased. I want to read you a quote here from a study done by Akamai back in 2009. It reads, "Consumers become impatient when pages take longer than 2 seconds to load. 40% of consumers will wait no more than 3 seconds for a web page to render before abandoning the site." And that's from a study in 2009 called 2 Seconds. There's another study they did back in 2006 called 4 Seconds. And unsurprisingly, back in 2006, the users were able to tolerate 4 seconds of page loading. So just in 3 years, our tolerance for slow pages decreased by half. And that was many, many years ago. So today, a more recent study by Radware, it shows that 1 second is now the gold standard. And they actually defined a new metric called time to interact. Time to interact is the time from when a user navigates somewhere to the first moment that they're able to engage with that site. The bar charts you see to the left show that as time to interact increases, the bounce rate, the rate at which people leave the site, increases very quickly, and additionally, page views also decrease very quickly. And since the revenue model of the internet is currently around page views and ads, that's the same thing as throwing away money or burning money. So size does matter. It matters because we've become less patient. We're more likely to leave a website if it takes more than 3 seconds to load. And the amount of time that a JavaScript parses a site is directly related to the script's time, and that is what's actually connected to time to interact. So if the JavaScript script is really long, the TTI for that site can be very high and cause people to leave. Simple matter of programming, probably my favorite saying in software development. It implies that any problem is solvable by simply writing more code. I think we all know that this is often not the case. But front-end developers are really smart people. And for years and years, they found ways to get what they needed done, workarounds and hacks. And there's a variety of best practices they can use on the front end to make a page more responsive. The primary tactics here are breaking that page into pieces and deferring the work that doesn't need to happen right away to a later stage. The problem with this, though, is it can take a simple website and make it incredibly complex. And if you're using lots of frameworks, like most websites do today, breaking that up can be challenging because the frameworks won't work that way. And the maintenance burden is much harder on the sites once they engage in this. So unless you have an army of developers like a big place like Facebook, you may not be able to take advantage of these tricks to make time to interaction better. So if this is a hard problem to solve from the front end, is there something we can do on the client, on the browser itself, to make it better? And to look at that, I want to actually profile the navigation to time to interaction pipeline. There's a really interesting URL here at the bottom called What Happens When. And this URL, if you go there, will show you all the very, very detailed steps of what happens when you navigate. But I'm just going to show you a subset of that here. If we navigate to facebook.com, the first thing that happens is we take that URL and we have to parse it into the domain name. That domain name has to be turned into an address, and that address is, we go there and make a connection. Once we're connected, we talk to the server and we decide after exchanging some information that we can trust them. And so we request the content on that site, and the server hopefully obliges us and sends down that content. The browser is then getting a steady stream of all the resources that compose Facebook.com, for example, and it has to parse those pieces before it can render it to the user interface. Profiling this process, it's the parsing stage that definitely is taking most of the time. So we will delve into parsing a little bit more detail. Parsing is 3 steps, primarily parsing the HTML, the style sheets, and parsing the JavaScript. Once again, the profiler tells us that it's a JavaScript parsing that can be a limiter in all of this. So I know that was really simple, right? So now it's time to get a little bit more complicated. We're going to follow this process along in more detail and actually follow it into the JavaScript engine. So the JavaScript pipeline has a variety of pieces. The first part is called the front end. And in here, the .js file is basically a string of characters, that source code that you wrote. That gets parsed. Parsing is the act of taking that string, breaking it up into tokens, and generating an abstract syntax tree, which is a data structure that represents your source code. It's then analyzed in a loop, and the AST, the abstract syntax tree, is refined to make it better as more analysis happens, so the code that we generate will be better. So since we're going to talk about ASTs a lot in the rest of this presentation, I thought an example might be handy. I started with this, what I thought was a simple JavaScript program, but then generating AST from that actually turned out to be quite large, so I reduced it to 2 lines. The AST is a representation of the program, so the first node in that tree is the program node. And in this case, we are able to verify that we have variable declarations, 2 of them. In the variable declarations are a equals 42. Here, you already notice that the AST is getting rid of unessential information that comes from the source file, like the delimiter, because the tree structure will represent the program structure, and the delimiters become unnecessary. The next part of this particular parse is the declarations have declarators, and that's the named identifiers that are being created in those declarations. We have two named identifiers, A and B, and they have an actual optional argument step here, initializing their the variable values with 42 and 5 respectively. So that tree structure is the AST for those two lines of code. Going back to our JavaScript pipeline, we are then able to take that finalized AST and generate bytecode. And that bytecode runs in the interpreter, and if we do a good job, it's running fairly fast. But we're watching that code all the time. If that code gets hot, if it's run more than 10 times, the JavaScript engine decides it's worth spending additional time to compile it using the baseline compiler. And what that does is it takes some part of the interpreted bytecode and actually replaces it with more optimized machine-specific assembly instructions. And that runs faster, which is good. If the code gets really hot, if that piece of code runs 1,000 times, then the engine will actually spend a lot of energy on really optimizing it as hard as it can using the optimizing compiler. And for Firefox, the optimizing compiler is called IonMonkey, and we generate Ion JIT code. And that runs even faster. It's actually the fastest we can go. But it's also very, very fragile. We make a lot of assumptions to build this long chunk of machine-specific assembly instructions. And if anything goes wrong or any of those assumptions are blown, we have to throw it all out. And we go right back to the baseline phase. For those who were here earlier today when David Bryant was talking about the browser JavaScript wars, this bottom tier is really where most of that fighting took place. The Octane benchmark was kind of the main benchmark at that time, and Google, Apple, and Mozilla Firefox all focused on building our compilers to be as fast as possible to generate code for that. But it turns out, for this case, the case of Facebook.com in 2017, the code rarely ever gets hot. So we're actually going to go backwards and focus on the front end. When you have a lot of JavaScript, it takes a long time to parse. And in the case of Facebook, that can be on a fast machine, between 500 milliseconds and 900 milliseconds. If you recall back to our quote from before, 1 second is the gold standard. And here we are, just in the parse phase, taking almost all that time that the website needs to load and interact, almost all that time being used up just in the parse phase. So we're not doing very well right now. There are techniques that exist that try to make websites with large scripts faster, and those techniques are compression, minification, and caching. Compression is applying a generic compression algorithm like gzip to the code, and because it's now smaller, it will flow through the internet and to the JavaScript pipeline faster. Unfortunately, it has to be completely uncompressed to its full size when it hits the parser, so it's not any faster in the parser. Minification employs a different strategy. Minification looks at a JavaScript source and gets rid of everything unessential and turns all the long, friendly identifier names into short, single variable names. That makes it smaller, and because the variable names are smaller, it's actually slightly faster in the parser as well, but it's not significant. Caching is actually quite a powerful tool. Caching allows us to fetch data from the disk instead of going to the internet, certainly speeding things up. And because caching's client-side, we can actually cache the bytecode. Chrome does this and Firefox does this as well, which can completely save on the parsing and code generation step. But unfortunately, caching only works if you've seen that code before. That it can be commonly the case for regular websites, but a website like Facebook might update every hour, and so this perfect warm load scenario doesn't happen as often as you would like. So there's another strategy that we can use to help with the time to interact called lazy parsing. And there's two different techniques that are currently used to lazily parse code. One is manual. That is, take your army of developers and you, once again, I mentioned this before, rip apart your application and only serve the most important stuff first, and then defer the parsing and the loading of all the other JavaScript till later. And this is complicated, but it can work. It doesn't actually make total parse time faster. It just defers the work to a different time. The other strategy is in some of the JavaScript engines, like V8 and SpiderMonkey, it's called syntax parse. What this is a fast first parse phase with no analysis, and it differs as much as it can. It helps to get the TTI down. Unfortunately, the entire JavaScript file has to be read. We're not smart enough, we don't know enough about a website to break it into chunks. So if you have 10 megabytes of source code, we still have to read 10 megabytes. And I think all websites grow in size over time. Nothing ever gets smaller. So the speed of a website will keep getting slower, even with lazy parsing. This morning, David Bryant brought up a new technology that we created at Mozilla called WebAssembly. It was designed from the ground up around speed and how to make applications on the internet as fast as possible. Some of the strategies it uses, it's very, very compact down the wire, so it's fast to download. And it has a very simple parsing step, single pass parser. Additionally, WebAssembly is defined all the way throughout, so you can actually skip the parsing and code generation phase by using ahead of time compilation. The problem with WebAssembly is it's not JavaScript. If you have a team of JavaScript developers on the front end, they will not be able to use WebAssembly to write their code. It's a completely different language. Additionally, even if they wanted to learn WebAssembly, they would have to rewrite all the work and start over. And WebAssembly suffers from some feature limitations that JS has, like no garbage collector in WebAssembly. So you wouldn't be able to easily map all the stuff that your website does to WebAssembly. So parsing is slow, and that seems to imply that we should write a faster parser. But it's not that easy. In fact, we already have. The parsers in the browsers today are all the latest, after many generations of writing faster and faster parsers. I don't really want you to concentrate on details here, but the problem is JavaScript itself is inherently difficult to parse, and I list some reasons, but an example might actually be a little easier to comprehend. In this example, it's really hard to tell where the start and stop points, the delimiters and tokens are just by looking at it with your eye. Writing a parser to do this is really, really complicated, and it will require you to go back and forth as you try to match the brackets and the where the comments are and where the actual identifiers are. JavaScript is not an easy language to parse, and it's not possible to write a fast parser for it. But we know parsing performance is a problem, and we know we can't write a faster parser. So I guess we're just sad, right? There's nothing we can do. Back in late 2016, the Mozilla JavaScript team, though they had an idea, they're like, well, if JavaScript is really slow to parse, we don't actually have to parse it. At least we don't have to parse it on the client. We can wait, or rather we can pre-parse it and parse it on the deployment server side. How would that work? You still have to send something to the client. If you pre-parse it, you have to have something at the result of that stage that the client then takes. So let's have another parsing example here. Say, I think relatively straightforward iteration function in JavaScript. And after being analyzed by SpiderMonkey, it will generate an AST that looks like this. This is a JavaScript literal form. It's more compact than that graph I did before, but trust me, that is the AST for the JS source we saw. What we can do is we can take all the nodes in that AST and make a node table. Just number them nodes, one through whatever. And we can take all the strings in that AST and number them, creating a string table. if we substitute the strings, if we substitute all the nodes with the node numbers, we get the AST represented as a long sequence of numbers. And the string table can just be written out as the index and the string that is there. And voila, we have a much tighter, smaller representation of an AST. So it's smaller, right? And if you save that string out as a binary file, you have a binary AST. Save it as a bin.js file, and that's where the name comes from. So why stop at the AST? I'm going to go back to our JavaScript pipeline. We had a source file. We parsed it to an AST. We decided this was a good place to pre-parse. Why don't we keep going and pre-parse to the bytecode? Or go the entire way and actually pre-parse to the machine code? To answer that question, this is what Facebook wanted to do initially. And we did look into that. It seems like a really fantastic thing to do. You'd save all that work by just doing it one time. But to answer that question, we're going to take a look at some of these data structures in a little more detail. This is the AST that we showed before. I think if you look at this for a while, you can convince yourself that it's a pretty easy mapping between the two. And the reality is, while every single JavaScript engine has their own AST, so long as the source language is the same, their ASTs tend to be the same. So it's possible to construct a unified AST that's optimal for all these implementations. The only key here is that unified AST will have to be designed and has to be standardized so we all can use the same thing. Is the same thing true for bytecode? Can we generate a unified bytecode that will work on all the browsers? This is a function with a callback to itself and the bytecode that SpiderMonkey will generate for it. And if you're familiar with assembly, you can probably sort of figure out what's going on. But I think what's more important for my purposes is, let's just take a look at that same thing in JSC, the Safari JavaScript engine, and you'll notice it's very, very different. That there's analogs for sure. If you spend some time looking at them, there's some similarities, but the implementation details of the bytecode come out in the implementation in the actual bytecode for an engine. And these engines are decades old, so they're not going to easily work out to use the same bytecode. We could force them to, but even if we did and we chose to standardize a bytecode, which is an idea people have had in the past, the bytecode changes a lot. Every single time you add new JavaScript features or make new optimizations, you often need new bytecode. And so the spec for this would have to churn, which is not ideal. The AST tends to be a lot more stable. Should we hold on to machine code? Well, machine code suffers from the same problems as the bytecode. In fact, more so, because machine code is machine-specific. So it has all the problems of the bytecode, but it also has the problem of the web server will have to hold on variants of every single client hardware that you care about, or you risk being slow with some browsers and some client hardware. Once you have a binary AST, there's other things you can do besides simply benefit from this pre-parse. It's possible to reorder the stuff that's in the binary AST. So it's possible to have things that happen first get generated first. Compression can also be applied, and the binary AST is pre-parsed process, so there's no analysis that's required. So you can generate an AST in one pass. The pros of binary AST are many. It's actually one of the few things that generally or genuinely improves parse performance. It doesn't require any coding changes. I didn't talk about what code you have to write at all to benefit from this, but there are some cons. You have to change your build or deployment stage to generate those new bin.js files by applying some sort of tool against your JavaScript files. And browser vendors will have to standardize on a new AST, and that has to go through the TC39 process. So there's some time involved in that work. So how would this work in reality once we have binary AST and bin.js files? You'd need to modify your build system if you have one, or deployment system, and run a command line tool on the JavaScript files you care about to generate a bin.js file. If you use something like Babel, Babel's already investigating adding this functionality directly, so almost get it for free. And on the browser side, you have to modify the browser to understand the new bin.js format and create a new optimized pipeline that bypasses parsing for the bin.js file. And once you have a bin.js tool, you can treat that bin.js tool like your other tools that you may apply on your JavaScript, like minification, obfuscation, or compression. You can apply any or all of these, or any combination of them, depending on what you want. If you want a binary.js file because you want the performance, but you still want it to be human readable in the debugger, you probably wouldn't apply obfuscation, for example. So what does the new pipeline for bin.js look like? Well, you have a bin.js file instead of a JS file, and it happens to be a series of bytes, because bytes are a tighter representation and faster to parse. A very minimal parsing phase that directly generates the final AST. And here we are looking at the completed pipeline that's complete, as I'm willing to show here. And it hasn't gotten any simpler. It's quite complicated. Adding a new pathway increases the maintenance burden for sure, and in fact increases the surface area for security vulnerabilities as well. Hopefully, though, the performance is worth it. So word on performance. Before I go any further, I want to say that, see if I can make this go back and forth a couple times, this is completely experimental. I mean, all the numbers I show you now may not happen in real life. It's a proof of concept. But I don't want you to say, hey, bin.js is going to save the world because of the numbers Naveed showed on stage today. So binary ST was made primarily to solve the problem of really large JavaScript files and loading them. So looking at a small website is not that interesting. We're going to look at Facebook again. Remember, Facebook on a fast machine might take as much as 900 milliseconds to load. A naive bin.js implementation could bring that down to a third, to 300 milliseconds. I mentioned that it's possible to apply reordering and other lazy optimizations to bin.js. And in that case, we were able to get all the way down to 1/6 the original parse time of Facebook.com. I think that's fast enough for us to sink some resources into this and see where it can go. This is not something that we've done alone. While Mozilla started this effort, Facebook asked us to take a look at this problem. So we're working with Facebook on this, and we also have a standard member in Bloomberg who is helping us with the specification. Speaking of specification, the path forward is one of standardization. It's only useful if every single browser implements this, and for that we need to come to an agreement, and that agreement really involves the TC39 standardization process. There's 5 stages in this process. The first one, straw man, basically is, I have a really cool idea. I want you guys to hear about it, and I want to take feedback. And this is where we were with Facebook back in early 2017. As of August 2017, though, we got our proposal accepted. And the key elements of this phase is the committee has committed to reviewing further changes to the spec, and that there's a list of champions involved, which I already showed you. We also have a demo. So the next stage that we're working to is it's called the draft stage, and here we want a completed experimental implementation that's actually in the browser, not in isolation like we have right now. We can't control the standards process, but we're hopeful that we can get to here sometime by the end of the year. As a browser implementer, probably the most interesting stage for me is stage 3. At stage 3, the specification is basically complete. You have a completed implementation, and this is usually the stage that we release it in the release browser. So at this point, I'd be pretty excited because we will have this in front of the world, and we'll be taking data from the world. And the final stage, stage 4, is when you take that data from the world, fix up whatever sort of issues you found, and say, hey, we're done. it's time to stop and maybe work on version 2. Anyhow, that is what I have on Binary ST. I have a bunch of resources in the slides. One thing I want to call out here is this is very, very early in the process. If you haven't followed a TC39 standard technology through before, this might be a good one to jump on so you can see it transition through the phases. It's also a good time to get involved. Thank you very much for your time. I'm Naveed. If you have any questions, feel free to email me or find me on Twitter. Thank you.
Thank you. Thank you, Naveed. Thank you very much.